Yeah. Okay. Hi, everyone. So thank you for coming. Before we start the session, please invite your friends to enroll in deep learning course. The statistical machine learning course is full in the next semester, I mean. So 25 out of 25, but for deep learning, there are only 18, I guess, 18 or 17, I'm not sure. 18 or 17 out of 25 have enrolled in the course. I appreciate it if you please advertise the course so people take it. Thanks. Yeah, winter. Thank you. So yeah, both SML and DL courses have been offered for winter. Okay, so let's continue. And by the way, I will teach it hopefully, if the department doesn't change their mind, but I will teach it hopefully. So last session we talked about principal component analysis, unsupervised principal component analysis, and direct PCA, dual PCA. We also talked about kernel PCA. We started supervised PCA, but we couldn't finish it. So let's restart from the start of supervised PCA using HSIC. As I said, we have two variants of supervised PCA. One variant is a bit boring. I don't cover it in this course. I refer you to our tutorial paper for that variant. So you can see the tutorial paper, unsupervised and supervised principal component analysis tutorial. In that, I have covered both variants, but I think that variant is a bit boring. That is the old variant. The newer variant is this, which is mathematically sound, and it's interesting. So what is that? First off, it was what year? I don't remember, but I think 10 or 12, 10 to 15 years ago, I'm not sure what year, you can see reference 21, that Sholkov et al. Proposed Hilbert-Schmidt independence criterion. You know Sholkov? Bernard Sholkov. No? I have said his name several times in this course. He's the god of kernels in machine learning. Okay, the god of kernels is who? Sholkov. Sholkov is a professor, god of kernels in Max Planck Institute in Germany. Okay, his lab is focused purely on kernels. So they propose, for example, they have proposed HSIC, they have proposed kernel PCA. Many of the kernel variants of the machine learning algorithms have been proposed by them. I'm not sure about kernel SVM. I don't remember whether it was Vapnik who proposed that or Sholkov, but I'm sure that kernel PCA was proposed by Sholkov et al. HSIC was proposed by Sholkov et al. Maximum mean discrepancy was proposed by them. Generative moment matching networks was proposed by them. All of these that I just said are using kernels. Also, distances in the Hilbert space, reproducing kernel Hilbert space, was proposed by Sholkov. As you see, he has done a lot. So what is Hilbert-Schmidt independence criterion? I said it in the previous session, but let me say it again. Assume I walk toward you, you go away. Come here, you come to me. Okay, and we do it several times and see this happens. So what does it mean? We are dependent on each other, right? And this dependence is linear because it's in the same direction, right? And as you do what I'm doing almost in the same direction, this is positive linear dependence, right? Linear dependence in statistics is also called correlation, right? So we have positive correlation. Now assume I come to you, you come to me. I go away, you go away. So it's still linear dependence. It's still correlation, but it's in opposite direction, and that's called negative correlation. So we have negative correlation. And as you see, calculation and verification of correlation is so easy. So easy, right? That's why correlation is used a lot in science, right? You hear that a lot. However, what about If I come to you, you go right there. I come further, you go there. I come back, you go there. It's not obvious whether we are dependent or it's completely random, right? Are we dependent or is it completely random? That's why nonlinear dependence is very hard to measure. So dependence in general is hard to measure, right? Correlation is easy. Now, what can we do to measure the dependence of two random variables? You tell me. So one way is this. Sholkov et al. Said, let's map data from input space to some other space named reproducing kernel Hilbert space, right? We talked about reproducing kernel Hilbert space in kernel SVM lecture, right? Let's map them in another space. In that space, reproducing kernel Hilbert space, let's calculate their correlation. Their correlation in the Hilbert space is a good estimation of their dependence in the input space. Interesting. Something which was hard to calculate in the input space became easy to calculate in the Hilbert space, right? So that's why this is exactly what the idea behind HSIC, Hilbert-Schmidt independence criterion. And why is it called Hilbert-Schmidt? Because these are the people who founded functional analysis in mathematics, Hilbert and Schmidt. And you know that reproducing kernel Hilbert space is all about functional analysis in mathematics. One of the hardest parts of mathematics, okay, pure mathematics. And first it was used first it was in pure mathematics, then it was used in quantum mechanics. Later it became into machine learning, right? By kernel SVM, by proposal of kernel SVM. So this is HSIC, empirical estimation of HSIC. You can see this reference for the paper of HSIC. And as you see, it's trace of, so what is KY? So assume this is the HSIC between X and Y. X is a data set, Y is a data set, right? So KY is the kernel for the Y data set, right? KX is the kernel for, you tell me, X data set. Okay. By the way, KX dot dot, I mean KX. That's, ignore the dot above it. Okay. Here I have said it. KX is the kernel over X data set. KY is the kernel over Y data set. What is HKY of H? It's double-centered kernel, right? What is KX is the kernel over X. So and what is trace of this times this? Trace of A transpose B or trace of AB. What is that? Recall preliminaries. That's the inner product between two matrices, right? So basically, and this we also have some scale. N is the number of points, right? So basically, it says that double center one of the kernels, and you also have the other kernel, calculate their inner product, and this is a good estimation for the dependence of X and Y in the input space, right? And H here is the centering matrix defined in equation 60. Recall preliminaries, we talked about it. Okay. And interestingly, when HSIC is 0, it means that they are independent. When HSIC is positive, it means that they are dependent. So HSIC is greater than or equal to 0, but there is no upper bound on that. That's the flaw of HSIC. Okay, there is no upper bound. But the larger the HSIC, the more dependent they are. Okay.
There are so many metrics to measure the dependence. For example, mutual information.
Yes.
So when do we choose? So how do we pick one over the other when we want to measure the dependence?
So the question is, for example, we have HSIC, we have maximum mean discrepancy, we have mutual information. Let me tell you about maximum mean discrepancy also. We have several measurements for calculating the dependence. Yeah. So maximum mean discrepancy, what is maximum mean discrepancy in parentheses? It's not related to this lecture. What is that? It's used a lot in machine learning, by the way. It's used in generative moment matching networks, for example. Maximum mean discrepancies, also proposed by Sholkov et al., says that assume I want to compare two distributions. right? And you know that every distribution has some moments. What do I mean by moment? What is first moment of a distribution? By the way, when I say first moment, I mean expectation of x. Second moment is expectation of x squared. Third moment, expectation of x cubed, etc. So you have moments until infinite moments. You have infinite number of moments, right? What is first moment? I just said it, expectation of x. What is expectation of x?
Mean?
The mean of distribution. That's good, that's fine. Expectation of x squared. Recall preliminaries. It's related to both mean and variance, right? So you can see it as kind of variance. Third moment shows the skewness, how much skewed the distribution is, etc. Right? So these are giving you the characteristics of the distribution. Now assume you want to compare two distributions. So there are several ways to compare two distributions. One of them is KL divergence, right? Another one is MMD, maximum mean discrepancy. What is it saying? It says that you can compare the first moments of the two distributions, but it's not enough. You need to compare the second moments as well, third moments as well. But you need to go until infinite, all of them moments, but you have infinite number of moments. It's too hard to compute the difference between all of them. So basically it says that let's bring them to the Hilbert space, the two distributions, to the Hilbert space. In the Hilbert space, you simply calculate the Euclidean distance between the points. That's a good estimation of the distance, difference of all of the moments in the input. That's called maximum mean discrepancy. It's very interesting. Interestingly, maximum mean discrepancy is equivalent to HSIC. So when they proposed HSIC, they also had proposed maximum mean discrepancy. Later, Sholkov et al. Themselves found out that they are equivalent. Okay, so they rediscovered something else in another formulation. So many of them are equivalent. First off, that's one answer to your question. Another answer is that we have different options. We should see which one is good for our purpose. For example, when we are working with kernels, of course, HSIC or maximum mean discrepancy are useful. Mutual information is not useful because we are working with kernels. For example, we will see that why it will be useful for supervised PCA. For supervised PCA, I can't use mutual information. I think supervised PCA of the variant one that I said is boring, kind of uses mutual information. But for supervised PCA that I'm explaining here, proposed by Ali Qudsi et al., they use these, and you will see that, we will see in a few slides that it's completely related to PCA itself. So you should see which formulation is useful for you, and then you use it. Okay. In this case, HSIC is useful. Okay. Now, let's talk about supervised PCA or SPCA, proposed in reference 22 by Ali Qudsi et al. In University of Waterloo, and some of his co-authors were in University of Shiraz. Okay, so in Iran. So uses HSIC. Okay. What do they do? So HSIC was proposed by Sholkov et al. They used it. They said that consider X as data and Y as labels. Okay. For generality, we assume that labels have the dimensionality L. When L is 1, it means that labels are scalar, right? Okay. The data is also d-dimensional. So I'm putting X and Y column-wise. So assume we also can do one hot encoding, then L becomes greater than 1, right? Do you know what one hot encoding is? Do you know that? If you don't know, let me know. Why don't you say so? So 1, assume 2, 3 labels. Okay, then I can say it as 0, 0, 1, 0, 1, 0, 1, 0, 0. This is class 1, this is class 2, this is class 3. One hot encoding, right? Every class, so the number of bits becomes the number of classes, and every class has one of the bits, right? Corresponding to that. And By the way, what is the usefulness of one-hot encoding in machine learning? This part is practical. Why? Why don't we use 1, 2, 3? Rather, we use one-hot encoding sometimes. It's because of their distance. See, 1 and 2 has distance 1, 2 and 3 has distance 1, but 1 and 3 have distance 2. That's an issue. Who says that class 1 and class 3 are further from each other than class 1 and class 2? Right? But when you do one-hot encoding, you will not have that issue. They will have equal distances, right? At least they have equal Hamming distances. So now you have these things. So now H-seq was a good measurement for dependence. What did the authors say? They said, okay, I have X, I have Y, right? Let me capture the dependence of X and Y. Okay, let me capture the dependence. I have data and labels. They have some dependence on each other. Okay, so as a result, what should I do? First, but by the way, they capture the dependence of projected data and labels. Okay, projected data by PCA or their algorithm is U transpose X, linear projection, right? Recall preliminaries. U transpose X is projection of X onto the column space of U, right? Recall preliminaries. So the kernel over the projected data is this: U transpose X transpose U transpose X, Benjamin transpose Benjamin, right? Kernel over Benjamin. So now trace applied on this. Trace reverses the order of multiplication. It becomes X transpose U transpose transpose becomes U, and also this, right? So this is kernel over X, kernel over Y. They also, so we have labels. We can calculate kernel over Y, right? Agreed. So we can either use linear kernel like Y transpose Y, where Y had the labels column wise, stacked column wise, right? Right, agreed. But this is good for regression when the labels are float or one-hot encoded or whatever. When the L, the dimensionality of labels, is greater than 1, maybe linear kernel is good enough. But when the labels are discrete and finite, so it's a classification problem, then it's good to use this kind of kernel, which is called Kronecker delta, right? I talked about Kronecker delta, I think, in the previous session. No, in the previous session of deep learning course. Okay, this is Kronecker delta. What is that? If yi equals yj, it's 1. Otherwise, it's 0. You see that? You see? By the way, we have two, as I said also in that session, we have two terminologies of Kronecker in mathematics. Don't confuse them. We have Kronecker delta, which is this. We also have Kronecker product. Okay. Kronecker product is between matrices. Google it later. Okay. They are different. Kronecker delta is used a lot in machine learning, is also used a lot in physics, in Einstein's general relativities. They use it a lot in differential geometry. Okay, so where were we? I said, okay, we calculate the kernels. Now, H-seq between them, right? I'm using H-seq, right? What was kernel over X? We just calculated that in the previous slide. X transpose U, U transpose X. What is KY? It's either the linear kernel, for example, or the Kronecker delta kernel. Do you remember? So now I drop this. This is a constant. I don't care about this. Factor, multiplier, right? So what should I do? I have projected data, right? By U transpose X. By the way, U is the optimization variable which I need to find, right? U is, in PCA, we also were finding U, right? Here in our new algorithm, we should also find U because it's a linear algorithm, right? Linear algorithm, it's linear projection. So our variable is U. We should say that which U we should find that the dependence of the projected data, which is U transpose X, and the labels becomes maximized. Did you get it? Did you get it? Hence, it is supervised because I'm maximizing the dependence between the projected data and the labels So I'm using labels. Labels with respect to U. Which U does that? So I maximize this HSIC. Of course, this maximization. If I just have this maximization without this, what happened? Can you solve it for me? Maximize this trace with respect to U. What is U? Without any constant. What is U? What is the solution? Isn't it obvious? If U is infinite, it becomes infinite. Okay, so there is no upper bound on U. So it is an ill-posed or ill-defined problem. As a result, we have to add some constraints so it becomes well-defined. The projection matrix, right? U is the projection matrix. So subject to U transpose U equals I want the projection matrix to be orthogonal also, or its columns to be orthonormal, right? Now we solve it. We have this optimization problem. How do we solve it? Recall preliminaries. Everything goes back to preliminaries. Lagrangian, right? Lagrangian. So this is this minus trace of, this is the constraint. I bring this to the other side. Trace because of inner product. Lambda is the eigenvalues. I mean, oh, sorry, not eigenvalues. We will see that it will be eigenvalues, but lambda here is the dual variables, Lagrange multipliers, right? Lagrange multipliers. So we do that, and now I have Lagrangian. I need to maximize it. What should I do? I take derivative, set it to 0, right? High school optimization, first order optimality condition. Derivative of Lagrangian with respect to U. U is d by p. As a result, this derivative is also a matrix. So you tell me, the derivative of this with respect to U is a quadratic function with respect to U. It becomes this. If you don't believe me, use a technique that I told you how to take derivatives, okay, in matrices. And this also is quadratic with respect to U. It becomes minus 2U lambda, set it to 0. This is 0 matrix. And bring this to the other side. These two 2's cancel each other. It becomes this. What is this? Guys, what is this? Consider this part to be Benjamin. Benjamin U equals U lambda. What is that? Benjamin times U equals U lambda. That's the eigenvalue problem for Benjamin, right? Thank you. So as a result, this is the eigenvalue problem for X, H, K, H, X transpose, right? Interesting. Where U are the eigenvectors and lambda are the eigenvalues. So it's a spectral algorithm similar to PCA, unsupervised PCA, right? Interesting. As a result, the projection matrix U has the eigenvectors of X, H, K, Y, H, X transpose, right? And we can truncate the columns of U as we talked about it before. So we have subspace, right? Otherwise, we will just rotate in the same space. For us to go into a subspace, the number of columns should be smaller. But how do we sort the columns? Of course, it is a maximization problem. Recall preliminaries. So we should sort the eigenvectors from largest eigenvalue to the smallest eigenvalue, right? And then we can get rid of the eigenvectors which have very small, tiny eigenvalues, right? This gives us a subspace. So again, as before, we have projection of training data, test data, reconstruction of training data, reconstruction of test data, as before, right? We can also have projection and reconstruction of test data for a matrix of test data, several test data, right? Now the beauty is here. Why is it so far it was some new algorithm. Now in the next slide, I tell you that this algorithm is related to PCA. That's why we can call it supervised PCA. Why? Why is it called supervised PCA? Because of this. Here is the proof. Not considering the similarities of the labels means that we do not care about the class labels. Agreed? Agreed? So as a result, if I set my kernel over the labels to identity matrix, it means that I'm not considering the similarities of the labels. What is a kernel of KY, kernel over labels? What is it saying? It says the class label of data point 1, for example, assume. What is KYIJ saying? Because KY is a matrix, right? I throw J's column. It's basically saying that what is the similarity of the label of ith point and the label of jth point. Agree? Now, when Ki equals identity matrix, it means that I don't care about the similarities of all points, and only every point is similar to itself, its label, right? Agree? Because it's diagonal matrix with diagonal 1, right? So if we do that, now, do you remember what was the solution of that new algorithm? Eigenvectors of this thing, right? This quantity. Now set Ky to identity, as I said. So it becomes, so H, recall preliminaries. H is centering matrix, which is symmetric. As a result, I can replace H with H transpose. We know identity matrix does nothing in matrix multiplication. So I have this. Now I have this repeated here. H transpose X transpose can be written as XH transpose, because transpose reverses the order of matrix multiplication. Agreed? Now, what is XH? Recall preliminaries. I'm tired of saying recall preliminaries. What is XH? Do you remember? It removes the mean of columns of X. And we know that we had put the data points column-wise. So as a result, it's centered data. Let's call it X breve, right? Centered data. The mean has been removed. So X breve transpose. And what is X breve transpose? We talked about it in the previous session. That's the covariance matrix before projection, right? So what was the solution of new algorithm? It was the eigenvectors of this. What is the solution of PCA, unsupervised PCA? The eigenvectors of covariance matrix. We just proved that when you set kernel over Y labels to identity matrix, the solution reduces to the solution of unsupervised PCA. As a result, when we have KY, this becomes supervised PCA. Interesting. Very beautiful. Very beautiful. Right? So, yes. For more reading about dual, by the way, do you remember we talked about dual PCA? Kernel PCA, do you remember? We also have dual supervised PCA. We have kernel supervised PCA, right? We can also talk about eigenfaces. What is eigenfaces? I will tell you. I will tell you briefly. But if I wanted to add all of these in the slides here, it would be 100 slides and it would overwhelm you. So I refer you to our tutorial paper, which has all of these things. Unsupervised and supervised principal component analysis tutorial. That also has been appeared as a chapter in our book, Elements of Dimensionality Reduction and Manifold Learning. Chapter, Principal Component Analysis. Okay? But what is eigenfaces? Let me tell you briefly. Did I say it here? No. So, in the area of face recognition, ancient times, around year 2000, 1990s to 2000, right? Ancient times, before the time of deep learning, etc. People were using PCA and these new linear algorithms for face recognition, right? So basically, what is it? Assume I have facial images. I have 10 facial images of Ben, 10 facial images of Alex, Jennifer, etc. So this is my data set. Okay. Now, by the way, when I say 10 different images of Ben, different maybe poses, different, I don't know, different variations of Ben, Alex, etc. Right? Then what do? We can, for example, if it is 30 by 30, I reshape them to become vector. 30 times 30 becomes 900, a vector of 900 dimension, right? Agree? Agree. Now, this becomes xi. Can I so I have a data set of vectors. I can apply PCA on it, right? PCA on it. So if I apply PCA on it, I will have some projection matrix U. Do you agree? Do you agree? I have some projection matrix U. And what will be the dimensionality of U? Can you tell me? What was the dimensionality of U? D by P if we have truncated the matrix U. Agree? Do you understand what I'm saying? Are you following me? No? Did you forget what I taught in the previous session? Okay, I have x's. I calculate the covariance matrix. So I have a bunch of data points, right? Vectors. I calculate the covariance matrix. What is the solution of PCA? The eigenvector of the covariance matrix, right? So I can get per U, matrix U, as the eigenvectors of the covariance matrix. What is a, so in when you apply eigenvalue problem, the eigenvectors become D by D, right? So it becomes, what is D here? 900. It will be 900 by 900 matrix, right? But I truncate that. Do you remember? I truncate it because of I want a subspace. I don't want to rotate in the same space. So for example, I truncate it to 900 by 10. Only the 10 eigenvectors having largest eigenvalues, right? Agree? So I have 10. Hi, that's fine. Come. No, that's fine. Good time. We are talking about eigenfaces. Okay, so I said we have some facial images and I apply PCA on them. It gives me some eigenvectors. Okay. Now I have assumed 10 eigenvectors, each of which is 900 dimensional. Can I consider, can I reshape every eigenvector to become an image 30 by 3 again, 30 by 30 again? Interesting. So we can visualize eigenvectors. If you do that, so you have facial images of Ben, Alex, Jennifer, etc., right? But when you do that, you will have some facial images. Eigenvectors will be some facial images which are vague. So they become like ghost faces, right? That's why it's called ghost faces in the literature too. Ghost faces. It's like horror movies. Okay, these ghost faces in when you are using PCA is called eigenfaces. Why? Because PCA uses eigenvalue decomposition. But when you apply Fisher discriminant analysis on that, specifically I'm talking about the year 2000, you will have Fisherfaces. Interesting. Okay. So eigenfaces were for 1990s. Fisherfaces was proposed in 2000. It revolutionized the thing, the area. And interesting, I think I have talked about it in the next lecture, I guess. But did you get the beauty? Did you see the beauty? It's very interesting. It's very. I assumed that my facial images are 30 pixels by 30 pixels. Okay. Acknowledgement, some slides are based on our tutorial paper on supervised and supervised principal component analysis tutorial. Take a look at that. I think it's a good tutorial. Or the chapter PCA in our book. And also teachings of Professor Ali Qudsi at the University of Waterloo. The code of I have coded PCA myself. You can see it in my GitHub page in Python. Also, you can use PCA in scikit-learn. By the way, PCA in my GitHub page, which I implemented, has PCA, dual PCA, kernel PCA, etc. Right? Supervised PCA has all of them. And these are the slides. Sorry, the reference. Any question? No? Let's move on to the next topic. And that's FDA. Fisher discriminant analysis. Is it possible to talk about PCA but not FDA? No. I believe Canada is one of the leading countries in AI. I believe. Because at least we have 3 big hubs in AI in Canada. Vector in Ontario, Mila in Quebec, Amy in Alberta. UBC, British Columbia, unfortunately, has not caught up to the other provinces for AI. I don't know why. I remember 6 years ago when I was applying, 7 years ago when I was applying for PhD, I went to UBC and saw there's no one working on AI. Why? But hopefully they have changed so far. But at that time, it was like a desert. I couldn't find, at least in some departments, I couldn't find many people working on AI. But that's why we have these 3 hubs. So for example, Amy in Alberta is focused on reinforcement learning.
Is she like?
No, Amy is just institution. Okay, so I think AMII, I guess. So Vector is led by many big names such as Hinton, but Hinton has retired. Brendan Frey. It's very good. Brendan Frey. By the way, if you didn't know that, Ali Qudsi was a student of Brendan Frey before, many times ago, many years ago. And
David Silver.
what?
David Silver.
I don't know.
Yeah, so he teach reinforcement learning, I think.
Okay. Yeah, sorry, I didn't know that.
Yeah.
And in Quebec, Mila is led by Yashua Bengio. Amy in Alberta is led by Richard Sutton, one of the biggest names in reinforcement learning. But we have some other people, in parentheses, let me tell you very fast because we don't have enough time. We have some important people in other countries too. For example, in US, Yan LeCun in University of New York and head of AI in Meta. Sam Royce, who was in Toronto, went to New York at that time, but he has passed away. He was working with Yan LeCun. In Stanford, we have Michael Jordan. Very good, very good. 10 years ago, Fei Li was very also hot in the area. I'm not sure about now, but 10 years ago, Fei Li in Stanford. In Stanford, Hasty Tipshirani, we have talked about them a lot. Tipshirani proposed lasso regression, lasso regularization. Hasty and Tipshirani are monsters in the area of AI in Stanford. So Stanford has a lot of good people in AI. I think Michael Jordan, I guess he is in MIT, I'm not sure. But yeah, these are the good people in US. There are a lot of others, but I don't know them much. In Germany, we have very good people too. University of Tübingen, I guess, has good people. Specifically, many of them are affiliated with Max Planck Institute. I just named one of them, Sholkov, right? I think Bernard Sholkov, god of kernels. Yeah. So, but there are other countries working on AI, but I think Canada is one of the biggest ones. So let's start feature discriminant analysis. FDA. Can we talk about PCA but not FDA? No, because they are siblings, right? They are siblings. Okay. First off, let me tell you that when we say FDA, many people, when they say LDA, they mean FDA. Okay. They are used interchangeably a lot in literature, but to be more specific, you know that they are different. I will prove to you that they are equivalent. LDA, we covered that in the previous sessions. That's a classifier, linear discriminant analysis. FDA is a dimensionality reduction algorithm. It's not a classifier. But how are they equivalent? Let me tell you in a nutshell that if you apply FDA and you go into the subspace of FDA and then you use Euclidean distance from the means of the classes in the FDA subspace, it's equivalent to LDA in the input space. I'll tell you why. Okay, the proof. That's why people use them interchangeably a lot. Okay. So first, let's talk about one-dimensional subspace. Assume we have two classes where superscript here shows the class index, okay? N1 and N2 denote the sample size of the first and second classes respectively, right? And if the data instances of the jth class are projected onto a one-dimensional subspace, then we will have U transpose Xij. Agreed? This is linear projection onto one vector, right? Vector U. Then, so the mean of the jth class also is Uj. This is the mean of the jth class. Nj is the number of points in the jth class. Agreed? Assume the mean. So Xi is this Xij. Okay. Assume I project it onto U transpose Xij. You tell me what happens to the mean mu j. The mean is linear, right? As a result, the mean also will become U transpose mu j. What about Sj, which is a scatter? A scatter is another name for covariance. Okay. Covariance is quadratic, right? So Sj becomes U transpose Sju because it's quadratic. Agree? By the way, we talked about this in the previous session about PCA too. We talked about it. Okay. Now, I want to calculate this. So after projection onto the one-dimensional subspace, the distance between the means of classes after projection. What is that? Do you remember what is the Euclidean distance? X minus y. You tell me. A squared Euclidean distance. Recall preliminaries. A squared L2 norm of Benjamin is what? No. Benjamin squared L2 norm of Benjamin is what? It was a formula, recall preliminaries. It was Ben transpose Ben. Right? So it becomes X minus Y transpose X minus Y. That's a squared Euclidean distance. This is a Euclidean distance, right? Agreed? And a squared Euclidean distance. This becomes this, right? But Euclidean distance itself has a square root. So far clear? So now here I'm using a squared Euclidean distance between the means of the two classes after linear projection. I will have this. Right? Agreed? So can I factor out U? Yes, I can factor out U. And because the order of matrix multiplication changes by transpose, U becomes here. So U becomes U transpose becomes U. Also, I'm factoring out U transpose. This is a scalar. The whole thing is a scalar. Every scalar is equivalent to its trace. Right? So trace, I can use trace here. Agreed so far? And now I can use cyclic property of trace. So I move these according to the cyclic. So I bring this here, and then I bring that again there, right? I will get this. It's a good technique. By the way, now this is also, the whole thing inside is still a scalar, so I can drop the trace now. I will have this. Did you see the technique that I just used? In this course, I'm not just teaching you the algorithms. The algorithms are just excuse. I'm teaching you techniques, okay? So that was a technique that you just saw. I have some scalar, but I need to reorder them somehow. I take trace, I use the cyclic property of the trace, and I drop the trace again. Hoping, but I will not be able to drop the trace again if inside is not a scalar anymore. But it is a scalar inside. Okay. Then this thing is, we define it to be SB. B is standing for between classes. B, between the two classes. And it's a scatter between classes, between a scatter. As you see, it's the scatter between the means of the classes before projection. So This was the Euclidean distance between the means of classes after projection, but SV is a scatter before projection in the input space. Okay, so far clear? Now consider dW. What is dW? Let it be the distance, or whatever you call it, the scatters of within classes. W stands for within. Okay, within. So in other words, the B between classes, you can see it as interclass. Within classes, you can call it intra-class. Okay, so I will have dW, let it be the addition of scatters of the two classes, U transpose S1U and U transpose S2U. These are the covariance matrices after projection, right? Again, I factored U and U transpose out. S1 plus S2, I define it as SW. So SW is the within scatters, summation of within scatters before projection. Okay. So within a scatter, also called intra-class scatter or intra-class variance. Between a scatter, also called inter-class variance, or yes. Now assume we have multi-class classes. So far we assume that we have two classes. What if we have several classes, more than two classes, right? Assume we have C classes, C class. In this case, I can say SB is defined as this. So there are several variants. Variant one is this. I calculate the mean of means of classes, which is equivalent to the total mean of the data. Okay, so far clear? Total mean of, let it be mu, the means of means or the total mean, right? Then I can calculate the scatter of the means of every class from the total mean. I call it SP and I sum over the classes. So far clear? Some people scale this SP by NJ. NJ is the cardinality of the J's class, the number of points in the J's class. Okay? So it gives us SP. Is what I'm saying boring? Because it seems that you are bored. Is it boring? Why don't you answer? Which part is boring to you? What? It's the easy part. We haven't yet reached the hard part.
That is the challenge. When I have had my interview, they asked about how to make the student get engaged when, especially for math heavy course, so students can easily get lost.
Where was the part that you got lost? Can you tell me? No, really. Where was the part that you got lost? Where was the part? Interrupt me whenever you get lost, okay?
That would be rude.
No, why? Why rude? I said you don't need to raise hand. Shout at me and say, I didn't understand this part. Okay? Interrupt me, please. Which part? You mean, did you understand until here? All of you guys, did you understand until here? Yeah. So now I have, so DB, I can say it as U transpose SPU. What is U transpose SPU? Do you agree that? So SP, I define it as this. This is my definition, okay? This is SP, equation 33. What is equation 3? Can you tell me? Mu1 minus mu2. What is mu1 minus mu2? A difference of the means of two classes. Mu1 minus mu2 times mu1 minus mu2 transpose. What is that? Covariance matrix. Do you remember? A scaled covariance matrix, the scale that we don't care. Okay? Covariance matrix between the two classes. Agree? If the two classes are very far away from each other, SP gets large. If mu1 and mu2 are close to each other, it means that the two classes are very confused, close to each other. SP becomes small because mu1 minus mu2 becomes a small. And SP is a matrix. right? So far clear? And why is it d by d? Because this is d by 1. This is d by 1. Right? Right? Did you understand? Did you also understand? Okay, so this part, what am I saying? So we calculated the between the scatter. Now if, so assume, consider this is one of the classes, this is another class. So this was between a scatter. I also have within a scatter. The scatter of every class. How spread every class is, right? So this is, assume S1 is the covariance matrix of class 1. S2 is the covariance matrix of class 2. SW is the summation of covariance matrices of classes. I call it within the scatter. So far clear? And what are these DW and DB? So do you remember I told you when you project X on U transpose X, what happens to the covariance matrix? Comes U transpose SU, because covariance matrix is quadratic. Now SB becomes U transpose SBU, SW becomes U transpose SWU after projection. So far clear? Please, I beg you, please interrupt me if you didn't understand any part. Okay? So now, do you remember what was SP when we had two classes? It was equation 3. Mu1 minus mu2 times mu1 minus mu2 transpose. Now what if I have 3 classes, 4 classes, multiple classes? I can change the formula to this. Equation 6. I can use, so I assume this is class 1, class 2, class 3. The total mean is here. So mu1 minus mu is this. Mu2 minus mu is this. Mu3 minus mu is this. And I sum over all of them. So it's a total between a scatter. So far clear? Of course, when the classes are far away from each other, SP becomes large. The elements of SP, because SP is a matrix. When they are close to each other, SP becomes a small. The value, the elements of SP. So far clear? Right? So now, likewise, SW, you can say that you sum over the covariance matrices of classes. Covariance matrix of class 1 plus covariance matrix of class 2, etc. So far clear? Right? So I have DB and DW. By the way, there is another variant that you can see it in the literature. What is the total scatter? So ignore the class labels. You have some data points. Do you agree that I have a covariance matrix of the whole data, ignoring the class? I call it ST. T stands for total. The covariance matrix of whole data, ignoring the class label, right? Now, it can be easily seen, prove that total scatter equals within a scatter plus between a scatter. Okay? Now, rearrange the whole thing. SP becomes ST minus SW. So far. So far, we talked about all of these things. Now, consider this case. Assume I have 2 problems with my eye. So, okay. I'm giving you some thought experiments, okay? My eyes are weak. I'm also colorblind. Okay, and let's play a game. I have some balls, blue balls and red balls on the ground. I want to separate them, but I have 2 problems with my eyes. One of them is that I'm colorblind. The other one is that my eyes are weak. Yes. First, I want you guys to help me separate these blue and red balls. Okay. Now you tell me. Consider my first issue, color blindness. How can you help me separate the balls?
change the color.
No, assume the colors can be changed. There are balls on the ground shuffled, red and blue. I want to separate them. I need your help. I'm colorblind. How do you help me? Just consider what? No, I don't do anything. I need your help. You do for me. What do you do? Yes, exactly. Exactly that's what I'm saying. What do you do? So your eyes are okay. I'm colorblind, and there are some shuffled red and blue balls on the ground. What do you do for me to separate them? That's exactly what I was looking for. You separate, you put the red balls next to each other, blue balls next to each other, right? So what are you doing by this? You're increasing the between scatter of the two red and blue classes. Did you get it? You increased, what did you do? So because these were red balls, these were blue balls, shuffled. What did you do? You just did this. You separated it for me. So that was class 1. That was class 2. Very confused. Between a scatter between them was very small. What did you do by this? Mathematically, you just increased the between scatter. So far clear? Now consider my second issue with my eyes. My eyes are weak. So weak that I see the whole thing as one big ball. What do you do for me?
Increase the distance.
Yes, increase the distance. You already did that. Still, I'm still very, very, very weak in terms of. You can do another thing too to help me.
Make it big.
Big? No, the other way around. You make every class smaller. You push these blue balls next to each other. You also push these red balls next to each other. So I see the whole blue balls as one ball and the whole red balls as one ball because I'm weak in eyes. So basically what you do is this. You put all of the blue balls here, red balls next to each other. So I see the whole thing as one ball and this whole thing as one other ball. What did you do? You just decrease the within a scatter. So far clear? So far clear? Right? So basically you did two things for me to separate the classes. First, you increase the between a scatter. Second, you decrease the within a scatter. Do you see the idea, the beauty of this idea? This idea, which was proposed by Ronald A. Fisher a century ago, in the previous century, dominates supervised manifold learning. Supervised dimensionality reduction, most of them are having the same idea. Let's increase the interclass variances and decrease the intraclass variances. So far clear? Very interesting. Even triplet loss, which is a bit new, has the same idea in neural networks. Okay? So that's one thing. By the way, Fisher, let me tell you about Fisher, Ronald A. Fisher. Fisher was a scientist in genetics. Okay? He was a statistician. Do you know Fisher? Ronald A. Fisher? How don't you know him? He proposed variance. The proposer of variance. He is the father of modern statistics. If we hadn't had Fisher in the world, the statistics would be completely different. Okay?
Okay. The definition of variance.
Yes.
Like expectation, variance.
But variance. He proposed variance itself. And did you know that? So he was obsessed with variance. Obsessed with. All of his works are about variance. ANOVA in statistics about variance. Fisher criterion, which I said about between variance and within variance. Variance itself about variance. You can see he has proposed several other things too. All of them about variance. So he was obsessed about variance. By the way, Have you heard of iris flower? No, yes, iris flower dataset in the machine learning. It's one of the very simplest benchmarks in machine learning. One of the, such as, how is MNIST famous? Iris dataset is also famous, okay? Very famous in statistics and machine learning. But it's a simple benchmark. It was proposed by Fisher, because Fisher was working on genetics of flowers and etc., right? So we have a lot of things have been impacted by Fisher. And I think he has been very impactful, that I guess either in University of Cambridge, I think Cambridge, University of Cambridge in UK, they have put something for him, some memorial. Yes. So that was, and now no wonder why Fisher discriminant analysis is about variances, right? So guys, please, you are not even looking at me. If you don't like this topic, I can change the topic. I can go to the next topic. Do you like it? Don't you like it? But this is an excuse, because at the end of this slide deck, I'm gonna teach you how to kernelize your own algorithms without kernel trick. So why did I cover kernel PCA? For you to learn kernel trick. In this lecture, I'm gonna explain kernel FDA to teach you how to kernelize your own algorithms using representation theory. I have explained this in the previous sessions. Yeah. There is no time much to, but kernelize means that you replace x transpose x with phi x transpose phi x, where phi is a pulling function from the input space to the Hilbert space. Yes. But for more information, see the lecture on kernel SVM. So, as I said, we maximize between a scatter, we minimize within a scatter. Okay. Can I say that? So, can I combine these two together? One way to combine them is maximize dB minus alpha dW. Because maximize minus alpha dW is equivalent to minimize dW, right? Alpha is some high regularization term. Another way is to maximize this fraction, dB over dW, right? Because maximization of 1 over dW is equivalent to its minimization, right? This is called Fisher criterion. dB is called U transpose SVU. We just talked about it. dW is U transpose SWU, right? This fraction is called Fisher criterion, proposed by Fisher. Okay. Interestingly, do you remember this? Do you remember this? This format? Recall preliminaries. We had it. What is this format? It's a generalized Rayleigh-Ritz quotient. Do you remember? U transpose AU over U transpose BU. We talked about it in the preliminaries. Okay? So it's a generalized Rayleigh-Ritz quotient. And do you remember, according to what we talked about in the preliminaries, it's that this maximization is equivalent to saying that maximize the numerator, but set the denominator to some constant, equal it to some constant. We proved that it is possible to do. Now I have this optimization problem. What should I do? Lagrangian, right? This minus lambda, this constraint, right? Now I have Lagrangian. What should I do? So far we had, I think, 30 times of this in this course, right? Lagrangians. Take derivative, set it to 0, right? Take derivative of this Lagrangian, set it to 0 with respect to u. It becomes this. What is this? Recall preliminaries. What is this? Do you remember? It's a generalized eigenvalue problem. Generalized eigenvalue problem, okay? Of SB and SW, recall preliminaries. So U is the eigenvector of this generalized eigenvalue problem, okay? As a result, the solution of Fisher discriminant analysis, this is called Fisher direction or Fisher axis, is the generalized eigenvalue problem of SB and SW. Interesting. Interesting. How can I solve this? There are several ways to solve this. One, what do you remember? We can convert generalized eigenvalue problem to an eigenvalue problem. How? This SB is a pain in the neck. Sorry, I apologize. This SW is in the pain in the neck. This SW. Lambda is a scalar. We don't care much, right? Here. So I left multiply the size by SW inverse. This goes away. I will have this. What is this? Benjamin U equals lambda U. It's the eigenvalue problem of Benjamin. So U became the eigenvector of SW inverse SP. This is a very famous formula in machine learning. Okay. So SW inverse SP. SW is the within scatter, SP is the between scatter. Now you tell me, what if SW is singular, is not full rank, is not invertible? Then how can I have SW inverse SP? One good technique is what? Let's strengthen the main diagonal of SW. So I add a very small positive number epsilon to the main diagonal of SW. This is a hack used a lot in Fisher discriminant analysis, right? Although, of course, too small epsilon may make it singular. Too large epsilon will make it inaccurate. So it's a trade-off. It's a trade-off. Okay. And again, we know that FDA was linear projection. So linear projection of training data and test data and reconstruction of training data and test data is as before, right? U transpose X and U transpose X. So far clear? By the way, as you see in Fisher discriminant analysis, we didn't have to subtract the mean. We didn't have to center data, but in PCA we had to. Do you remember? Yes. Do you remember variant 2 that I talked about? We have S total scatter. So I can replace SB by ST minus SW, where ST is the total scatter. Now I can write this numerator as this, break it down. So I can break down this fraction into two fractions. And interestingly, this fraction is 1. So it becomes this minus 1. Okay. Then, so I need to maximize this. This is constant, goes away. So maximize this fraction, right? This fraction also is another variant of Fisher criterion. It's a Rayleigh-Ritz, generalized Rayleigh-Ritz quotient. So I can say maximize the numerator while you set the denominator to some constant. Again, if you solve it, Lagrangian, etc., you will end up with this. So U can also be the generalized eigenvalue, eigenvector of STSW, right? Rather than SBSW, it became STSW. Now what if, so far U was a vector. Now assume I want to consider several dimensions for my subspace, Fisher this dimension discriminant analysis subspace. So I will have a projection matrix U, and my DB now becomes U transpose SPU, but U transpose SPU is a matrix. So I use trace for it, right? DW also U transpose SWU, but I use trace for it. So far clear? This DB over DW now has trace, as you see. Again, this is a fraction, which is a scalar. This is Fisher criterion for multi-dimensional, for multiple dimensions. Okay. Now I want to maximize this with respect to matrix U this time. What should I do? Maximize the numerator. It's a Rayleigh-Ritz, generalized Rayleigh-Ritz coefficient, right? This is approximately equivalent to this. Maximizing the numerator, where subject to denominator equals identity. Do you remember? Recall preliminaries. I said to you that when it is U is a vector, this is exactly equal to that. When it is a matrix, it's approximately equals. I talked about it in the preliminaries. Okay. Again, I need to maximize this. So Lagrangian, take derivative with respect to the optimization variable, which is U, set it to 0. These two 2's cancel each other. You will have this. What is this again? The generalized eigenvalue problem SB SW. Right? And what is U? The eigenvectors of this generalized eigenvalue problem. And it's not, this time it's not eigenvector, one eigenvector, it's multiple eigenvectors. And then we try, by the way, we should sort the eigenvectors from the largest eigenvalue to the smallest eigenvalue because it is maximization problem, right? And then we can truncate some of the columns of U so it becomes a Fisher subspace, right? Again, we can make it an eigenvalue problem by what we just talked about before. So we can say Fisher directions are the eigenvectors of SW inverse SP, right? We can also say that. Again, we can strengthen the main diagonal so for it not to be singular. Again, we have linear projection and reconstruction as before, but this time U is a matrix, right? This part is also important. So do you remember I told you that what was the solution of Fisher discriminant analysis? It was eigenvectors of SW inverse SP, right? Let's talk about SW inverse SP. It's rank. Rank just is rank. Every matrix has some rank in linear algebra, right? Rank of SW inverse SP, according to the linear algebra, it's minimum, it's less than or equal to minimum of rank of this times and rank of this. So because it's a matrix multiplication between SW inverse and SV, so it's less than or equal to minimum of rank of SW inverse and rank of SV. What is rank of SW inverse? What is SW? It was a within a scatter, right? So otherwise, in other words, it's covariance matrix. What is rank of covariance matrix? Let's discuss it. It's very important. The things that I'm telling you are not just for machine learning. It's for a lot of different things. And I think you will see the value of what I'm saying in the next years, the future years. You will see that. This is covariance matrix, right? Can you tell me what is the rank? Consider this for now inside the summation. Ignore the summation. Xi minus mu, this is d dimensional, d by 1. This is d by 1. So the whole thing here is d by 1. This is 1 by d. The whole thing is d by d. Agreed? The rank of a d by d matrix is what? You tell me. The rank is minimum of d, right? Is d. You can see it as d. You can see it as d. Minimum of d and d, which is d, right? But there is a but. It's not d actually. Can you tell me why? What is the rank? It's not D. Although it's D by D, but the rank is 1. Do you know why? The rank of inside is 1. Because it's a matrix 1. How did we find this matrix? D by 1 times 1 by D. Because of this 1. They are vectors. Right? So the rank is 1. Okay? You understand what I'm saying, right? Let's consider this A, B. This is D by D. This is D by D. The rank becomes D. The rank of C becomes D. Now compare it with A times B. A is D by 1. 1 by D. The rank becomes 1. So obvious, because this is a matrix, dense matrix, fat matrix, times a fat matrix. Of course, its rank is fat. It's a vector, tiny vector, thin vector, times a thin vector, although it's D by D, but the rank is thin, 1. So far clear? So far. So I have summation n times summation of a bunch of rank 1's matrices. What does it mean? Rank 1 plus rank 1 plus rank 1 n times. So the summation becomes rank n. Agreed? So the rank of covariance matrix is n, right? No. The rank of covariance matrix is not n. It's n minus 1. Can you tell me why? For this, for you to understand, consider an extreme case where n is 1. What is S? S becomes what? X. I have only 1 point, X minus mu, X minus mu transpose. When I have only 1 point, mu becomes, the mean becomes X itself. I have 1 point. The mean of 1 point is that point. So mu is X. X minus X is 0. So it becomes 0 times 0 transpose. It becomes 0. So when n is 1, rank is 0. So using induction, when n is n, the rank must be n minus 1. Did you get it? Did you get it? Because the covariance matrix of 1 point is rank 0. Because of this minus mu, I have this minus 1 in rank. Okay. So as a result, SW is D by D, but I also said that rank of covariance matrix is n minus 1. So its rank is minimum of D and n minus 1, right? Rank of SP is minimum of D and C minus 1. Why? Because the summation in SP was over the classes, right? Over the classes. So C minus 1. But the summation of SW was over the endpoints, right? Now I have this as a result, mean of mean becomes mean of D and n minus 1 and C minus 1. Usually D is large, n is larger than the number of classes. How many? Usually the number of classes is less than the number of points and the dimensionality, usually, right? As a result, the rank becomes C minus 1. Right? What does it mean? It means that when you find the eigenvectors of SW inverse SP, only consider the C minus 1 eigenvectors, the eigenvectors of largest eigenvalues. The rest are useless. Okay? So for Fisher discriminant analysis, we don't need a scree plot like PCA. For Fisher discriminant analysis, we know how many eigenvectors are enough. C minus 1. C is number of classes. What does it mean? If I have binary classes, I will have only one eigenvector. The other one will not be important. Right? Interest. When I have 3 classes, 2 eigenvectors. Interesting. We can compare FDA and PCA. Can compare them. So do you remember one of the variants of FDA was this? Maximize total scatter subject to within a scatter is identity. You remember? PCA, recall the previous session. It was maximize total scatter subject to U transpose U equals I. So U projection matrix is orthogonal matrix. The only difference is this constraint. Do you see the difference? Here, SW is considering the labels, class labels. So that's why FDA is supervised, but PCA is not supervised. Do you see that? So basically it says that let U be kind of orthogonal, but after some transformation by SW. Do you see that? Very interesting. But when also the PCA and FDA directions can be any in relation to each other. For example, in this figure A, they are perpendicular to each other. Why? Can you understand why PCA is this, FDA is this? Consider these two classes. What is the direction of PCA? The direction of most variance of data, right? Of course, this is the most variance of data. What is the direction of FDA? The direction of most separation of classes. This is the most separation of classes. In this case, they became perpendicular. In figure B, interestingly, they become equivalent to each other. This is the direction of variance of data. At the same time, this is the direction in which the classes are separated the most. Right? In figure C, they are neither equivalent nor perpendicular. Okay? Interesting. Now let's see why people use FDA and LDA interchangeably in the literature. Even in scikit-learn, there is the same library, LDA for both LDA and FDA. Okay. FDA is also referred to as linear discriminant analysis, LDA, or Fisher's linear discriminant analysis, FLDA. So what is that? FDA is a manifold or subspace learning method. LDA is a classification method. Okay. However, LDA can be seen as a metric learning method. Okay. Do you remember in the LDA lecture, I talked to you about that. I showed to you that LDA can be seen as metric learning. You remember that? So metric learning is also a subspace learning method. So there is some connection between FDA and LDA. Okay. So consider one-dimensional projection vector of FDA. X becomes U transpose X after linear projection, right? And we know that its mean becomes U transpose mu and its covariance becomes U transpose sigma U, because covariance is quadratic, but mean is linear, right? Now consider the Fisher criterion. What is Fisher criterion? Between a scatter over within a scatter, right? So U transpose mu2 minus U transpose mu1 squared is the scatter between classes after projection, right? U transpose S is sigma 2U plus U transpose sigma 1U. I'm assuming I have two classes, right? Is the summation of within the scatters, right? Now I factor out U transpose and U. Also here I factor out U transpose. I will get this. Okay. So this is what we had. I'm repeating it. We know that FDA maximizes this Fisher criterion. Agreed? Again, according to preliminaries, this is equivalent to maximize the numerator while you set the denominator to some constant. Okay. Well, now I have this optimization problem. What should I do? Lagrangian. Lagrangian is this minus lambda, this constraint. I bring one to the other side. Lambda is a Lagrange multiplier or dual variable, right? What should we do? Take derivative of Lagrangian with respect to optimization variable and set it to 0. You do that, then these two 2's cancel each other, you will get this. Okay, what is this? This is a generalized eigenvalue problem, this. Recall preliminaries. Okay? So far, did you follow me? Okay. Now, of course, U is the eigenvector of this generalized eigenvalue problem. But do you remember? I told you that I can convert it to an eigenvalue problem. SW inverse SP. Do you remember? So you can say that the eigenvector, the solution is the eigenvector of this inverse this SW inverse SP, right? So U is proportional to this equation 52. So far clear? On the other hand, interesting. Recall LDA lecture. What was the decision boundary of LDA? I think you studied that for midterm exam. Do you remember? It was equation 53. We talked about it in the LDA lecture. Okay, pi 1 and pi 2 are the prior distributions of the two classes. Sigma is the covariance, total covariance. Do you remember in LDA we assumed that sigma 1 equals sigma 2 equals sigma. The covariance matrices are equal to each other, right? Now, let me think. Okay, now use this assumption of LDA in equation 52, which we found for FDA. So sigma 2 is sigma, sigma 1 is sigma, it becomes 2 sigma inverse times this, right? 2 in I'm talking about proportional. 2 is not important, goes away. I have this. I know in FDA I have linear projection, U transpose X, right? I just found U is proportional to this. As a result, U transpose X is proportional to this where I have X at the end, right? So now compare these two. This is the decision boundary in LDA. This is projection, linear projection in FDA with the assumption that we had in LDA, right? Aren't they similar? Ignore this part. This is a scaling factor. Isn't this part very similar to this part? It is very similar. Sigma inverse mu2 minus mu1. Here I have sigma inverse mu2 minus mu1, but also I have mu2 minus mu1 transpose. So it's kind of quadratic of this. But again, this is linear projection of X. So up to a scale, which is where a scale is not important here. Up to scale, these two are equivalent to each other. The result, they are equivalent. That's why we use them interchangeably in the literature. In other words, FDA followed by the use of Euclidean distance for classification in the subspace is equivalent to LDA. So if you apply LDA in the input space, it is equivalent to applying FDA and project data in the Fisher subspace, and in that subspace you use distances from the means of classes, Euclidean distances from the means of classes for classification. Did you understand what I'm saying? Eigenfaces versus Fisherfaces. This is the ghost spaces that I was talking about. Okay. So as I said, can assume I have some facial images. Its projection matrix is U. So I have projection matrix U in PCA. I have projection matrix U in FDA, right? Every eigenvector in U I can reshape it to become an image again, right? So each of these is one of the eigenvectors in, each of these is one of the columns of U, which is reshaped to become an image, okay? This part is for Fisher, this part is for PCA, okay? And Fisher Eigenfaces was proposed in 1991, Fisherfaces was proposed in 1997. An interesting thing I haven't yet said. This, I have trained them, I have trained PCA and FDA on facial images where classes are, class labels were two classes. One class didn't have any eyeglasses. The other class had eyeglasses. Okay, so far clear? So the distinction between the two classes was eyeglasses. I had males, females in both classes. I had different things in both classes. The only difference was having or not having eyeglasses. PCA doesn't care about class labels. Doesn't use class labels. Let's take a look at its eigenvectors. It has captured different facial characteristics. One of them, this one, has captured hair, right? This one has captured cheeks, face cheeks. This one, maybe this part and this part. This one, mouth and also eyes. This one, I guess, a bit of nose. This one, the cheeks under the eye. And also, what was it called? Forehead. Different parts, as you see. This one, the whole face. Do you see that? By the way, they are in order of importance, okay? According to their eigenvalues. Now compare it to FDA. Eyes. If you, I don't know if you can see it well or not. Eyes, I can see eyes. It's very not obvious, but it's also eyes. Eyes have been captured in FDA. Why? Eyes and under eyes. Do you see the under eyes here? Here, under eyes. Because when you look at the under eyes, you can see either eyeglasses or not. The border of eyeglasses or not. Did you understand? FDA only cared about eyes for separation of classes. Eyes and around eyes. PCA cared about different characteristics of the face, so it finds the most variant direction of the faces. It says that which features separate the facial images regardless of classes. For example, if we have some facial images which have red hair, some which have black hair, of course, one of the eigenvectors will capture hair. Long hairs, short hairs. One of the eigenvectors will be hair. Females, males. What is the difference between facial images of males and females? That will be captured in eigenvectors. Maybe lipsticks, whatever, I don't know. Lips will be captured. All of these will be captured in PCA. But FDA says, what is the distinction between classes? Do you see the beauty? Interesting. Kernel FDA, let's have it after the break. Let's have a break until 7 or 8 to 9. Is it good? 7 to 9. What? 15 minutes of break? No? Until 9? I will not be able to cover the whole thing. You want? Till 9, whatever you want. I don't want to push anything. Are you enjoying the topic? When I explain math, I explain the intuition behind them. So far in the course, I have done that, right? I don't only talk about mathematics. Otherwise, it might become boring for you guys. I have watched a lot of YouTube videos about different topics. Many of them were pure maths. They didn't even talk about intuitions. But I'm trying my best to explain the intuitions and everything.
Yeah, I understand the intuition, like through your PhD study, or yeah, I take off courses. Not every professor teach like this because they may even don't understand the intuition behind that.
I passed different courses. I read a lot of papers. I studied different subjects. I believe you shouldn't. Have you noticed that I talk about philosophy? Because I have studied philosophy too. I sometimes, I don't know what differences. So I'm saying that you can learn different subjects and they will be useful for you to understand the other subjects. They might seem completely unrelated, but I think they're totally related. You can relate the philosophy of Spinoza to machine learning. I believe you can. I in the lecture of regularization of deep learning, I specifically talked about the for regularization of deep learning, I talked about Buddhism. Okay, so they are very related, very related. You can even, I have recently probably put a paper in arXiv named Amphilomatics and Psychomatics for combining philosophy and psychology with mathematics. Okay, and I believe that you can mathematically formulate many of the philosophies. Philosophy of Buddhism, Hinduism, Immanuel Kant, Descartes, etc. They can be formulated in mathematics. Maybe many of them are game theory, many of them are optimization problems. Even what Freud has said in psychoanalysis can be modeled mathematically. Many of them, I believe. Yes.
How do you figure out so many
I just said I try to learn different topics and kind of relate them to each other. This is how, and also I'm trying to learn this from different people. So I passed different courses. I watched different videos on YouTube. For example, how many courses should you pass? 9 courses. Go and sit in other courses too. Who says you should restrict yourselves to 9 courses? Do we? In PhD in U Waterloo, we had to pass 4 courses. I think I passed, I guess, 7 to 9 courses. I guess during my PhD. Many of them were audits, official audits, but I did it. I went additional because I wanted to learn. So I'm saying that don't restrict yourselves to bureaucracy or whatever they want you to do. Go and sit and learn. If there is no space, sit on the ground. In the course optimization for data science in University of Waterloo Department of Computer Science, the whole semester I was sitting on the ground. Because the course was full, there was no seat, only seat in the back seats. I couldn't sit there. I used to come and sit on the ground because I wanted to learn. Right? Okay.
department and university?
Okay, so now we talk about kernel FDA. Kernel FDA is excuse. I want to teach you kernelization by representation theory. I myself have proposed several papers where I kernelized my own methods using these techniques. Okay. So equation 3 in features. Do you remember equation 3? It was the SB between two classes. It was mu1 minus mu2 times mu1 minus mu2 transpose. But now we've pulled them to the feature space, to the reproducing kernel Hilbert space. For more information on Hilbert space, look at the lecture of kernel SVM. So phi mu1 minus phi mu2, phi mu1 minus phi mu2 transpose, which gives us phi SB, it is T by T, where I assume that Hilbert space is T dimensional and T might be infinite. Okay. So the mean of the jth class in the feature space becomes this. Phi of mu j is mean of the pooled data in the feature space. Okay, nj is a cardinality of the jth class. Okay. Now, here it is important. According to the representation theory, that's a field of mathematics. Okay. Any solution or direction, because solutions were directions, right? U. Now it is in the feature space phi of u. Okay. Any solution direction must lie in the span of all the training vectors mapped to the feature space. What does it mean? So those points are phi x, right? Phi x1 to phi xn. And usually t is much greater than d. D is the dimensionality in the input space. T is the dimensionality of feature space. Okay. By the way, don't panic by this sentence. It's very easy. I will explain it to you. So what does it mean? This means that, again, let me say it slowly. Any solution, phi u, u is the solution, phi u is a mapped solution, right, to the feature space. So far clear? Come with me step by step. Okay. Any solution must lie. Lie means exist. Okay. Must exist in the span of all. What does a span? Recall that preliminaries. I talked about the spanning. So for example, this space is spanned by 3 basis vectors, right? Span. So the basis vectors span the space. Okay. So must lie in the span of all training vectors mapped to H. So all training vectors mapped to H are what? Phi x1, phi x2 until phi xn. Agreed? So far clear? Then when I say a span of all of these, what do I mean? A space whose basis vectors are phi x1, phi x2 until phi xn. So far clear? Did you get it? Span. So when I say this space is spanned by 3 basis vectors, what does it mean? Every point in this space is a linear combination of these basis vectors. So far clear? That's phi. Every phi u in this space is a linear combination of phi x1 to phi xn. This is linear combination, right? And in linear combination, we have some factors, multipliers. Theta 1 to theta 1. In other words, theta 1, phi x1, plus theta 2, phi x2, plus theta 3, phi x3, etc. Every phi x is a vector. Theta is a magnitude. Right? Did you get it? This simple formula is kernelization by representation theory, and we'll see how it kernelizes the algorithm. We'll see that. By the way, I can write it in matrix form. Phi x theta, where theta is a vector of theta 1 to theta n. A phi x is a matrix having phi x1 to phi xn as its columns. Okay. So what if I have several solutions rather than one solution? I will have phi u matrix. So I have p solutions, p directions, right? P here is P will be the dimensionality of Fisher subspace. Okay. P is less than D. Okay. So phi u is T by P then, right? It has phi u1, phi u2 until phi un as its columns. Then this becomes this, but theta becomes a matrix this time rather than a vector. Theta becomes n by p. Theta 1, theta 2 until theta p as its columns. So far clear? Okay. Why should it be n by p? Because phi x is T by n. T is the dimensionality of Hilbert space. As a result, theta must be n by p. So phi u becomes T by p. Okay. Now, please bear with me and you will see the beauty. Okay. So what was dB in the Hilbert space? Phi u transpose phi sb phi u. I have pulled everything to the feature space, right? Because beforehand it was u transpose sbu. Now I have phi u transpose phi sb phi u. Right? Now you tell me, what was phi SB? We just talked about it. Phi SB, according to this equation 57, is this. Phi SB, right? What was phi U in the previous slide? We just talked about it. Equation 59 is phi X theta. As a result, phi U transpose becomes theta transpose phi X transpose, because transpose reverses the order of matrix multiplication, right? Now, do you see what I have this multiplication? Theta transpose, phi X transpose, phi mu 1. For the jth class, I will have this. Theta transpose, phi X transpose, phi mu j, right? J goes from 1 to 2, right? Okay. In a scalar form, this was a matrix form. In a scalar form, I can write it as this. Summation theta I, phi X I transpose, phi mu j, right? Right? Now what is it? Now, give me a second to think. Okay. What was phi mu j? Previous slide. Equation 58. Equation 58. So I replace phi mu j with equation 58. I will have this. One of these summations, this is because of this. This summation is because of the summation inside phi mu j. I'll have double summation, right? By the way, bear with me and don't get tired, because we'll have a lot of summations in a few slides, okay? But you need to be patient, okay? So now, interesting that here I have phi transpose phi. According to the kernel trick, that's the kernel. So I can replace it with the kernel, right? Agreed? Did you see how representation theory helped us to do kernelization? In kernelization by kernel trick, I already had it directly and I replaced it with kernel. In representation theory, in kernelization by representation theory, I don't have it directly. I make it. I generate it. And then I use kernel trick. So how do I make it? I use this formula. I say phi, I have u in my formulation. I replace phi u with phi x theta. As I have linear projection u transpose x, please listen to me. This is very beautiful. I have u transpose x, right? U becomes phi u, x becomes phi x. As a result, I will have phi u transpose phi x. But I don't have phi x transpose phi x. I can't use kernel trick. What does kernelization with representation theory says? It says I can replace phi u with phi x theta. Now substitute phi u with this. It begins do theta transpose phi x transpose phi x. Now it appeared. It is kernel. Because of this simple transpose. And this happened. Phi u was phi x theta according to representation theory. But I have phi u transpose phi x. So phi u transpose becomes theta transpose phi x transpose. I also had phi x from here. Interesting. Phi x transpose phi x appeared, which is the kernel. Did you see the beauty? This is the second type of kernelization in machine learning. It's very interesting, very beautiful. I myself published a method where I kernelize my method using these things. Okay. So now if I define mji as this, I can replace this with, write it in vector form, theta transpose mj. What is mj? As you see, is kernel between xi and so kernel between all of the points and the points of the jth class. Do you see? So basically, what does it say? It's average. It says on average, how similar the points of the jth class are to all of the points in the data. You see that? And it is n-dimensional. By the way, after kernelization, so before kernelization, most of your variables are d-dimensional, right? After kernelization, most of your variables become n-dimensional, where n is the number of points. I think it's obvious because kernel is usually the matrix of n by n. So before kernelization, usually you just deal with d-dimensional vectors. After kernelization, suddenly you are dealing with n-dimensional vectors. Interesting. Now, if n is large, you will face a problem. Beforehand, when d was large, you would face a problem. Now, when n, the sample size, is large, you will face a problem. I think it's obvious because when n is large, the kernel size will be very big and you will have memory error, right? D theta, so these are what we had. I'm repeating them. Equation 62. What was that? It was this. Becomes this. So according to what I just found, we know this is theta transpose mj, right? We also had these multiplications here. So if you put what we just found here in equation 62, you can write dB as this. Now let me define this middle part as m. They do that a lot in machine learning. Okay, they do that a lot. So you define this as m, which is n by n, because this is m by 1, and this becomes 1 by m. This is n by n, but its rank is 1. Its rank is 1, right? So it becomes theta transpose m theta. As a result, dB, which is the numerator of my Fisher criterion, becomes theta transpose m theta in the feature space, in the Hilbert space. Right? Interesting. By the way, what is m here? M is m1 minus m2. What was m1? On average, how similar my points of class 1 are to all other points in the data. Right? When you talk about kernel is similarity. You know that, right? Kernel is phi transpose phi. Phi transpose phi is inner product. Inner product is a measure of similarity. Recall cosine similarity. So whenever you say kernel, your mind should go towards similarity. Right? Phi SV, let's replace everything that we had by phi. So we had this formula without phi for FDA. Now we have a lot. We pull everything to the feature space. DW now becomes phi u transpose phi SW phi u. Okay. So phi u transpose, where was that? Okay. Phi u, according to the representation theory, recall we had that. We can write it as this, right? But it has transpose, so transpose is applied on this vector. Theta is a scalar. Transpose doesn't do anything on it, right? So this is what we had, phi SW, and this is phi u according to representation theory. This is what I said. You need to be patient in these slides a bit. You will see a lot of summations. I think we will have 6 summations back to back, I guess. We'll see that. So put all of the summations next to each other. Let's see what these summations are for. The first summation over the classes, the second one over the points, the third one over the points of the jth class, the fourth one over the points again. Okay. Why do I have double summation over the points? Because kernel is double summation over the points, right? And so in other words, in programming, this is 4 for loops, nested loops. Okay. So I'll have these, and now you tell me. I'm replacing phi mu j here and phi mu j here with what we had as a formula in equation 58. Do you remember that? Phi mu j. So I replace it here and here. Right? it became too long that I couldn't write the whole equation in one line. So I broke it down into 2 lines, right? Now it becomes more interesting. So this is what we had. I'm repeating it. Okay. Now you tell me. By the way, if you can kernelize your algorithm similar to these things, as it becomes too complicated, the reviewers will not understand it and they will accept you. Okay. That's a good technique. Okay. Okay, now that was a joke, but based on reality. Where were we? Give me a second to think. I don't remember what we had done here. Give me a sec. B. Oh, okay. Do you see that here? I have KZ, XZ, XK, kernel between them. It is equivalent to kernel between XK and XZ, because kernel is symmetric, right? Because kernel function is symmetric, I mean, kernel function. So this is this, and then what do I do? Give me a second to remember. Okay, I'm multiplying the terms together. So I have these 4 terms. This times this times this times this times this. I will have 4 terms, right? It gives me this. So far clear? And then what do I do? Interestingly, these two, no, give me a sec. Give me a second to remember. What was this part for? Okay, I don't know why this happened, but ignoring this squared, I should think about it. There is no time for me to go over to think about it. But if we ignore this, these two terms can cancel each other, simplify each other to become minus one of them. Okay, but I don't remember why nj is squared in the denominator of this one. Okay, if you study it later and find it out, let me know either in the comment of YouTube or let me know offline. But yes, it becomes simplified to this one. And then okay, what am I doing now? This summation, I bring it out and I put the whole thing. So these 3 summations, I can apply it once on this and once on this, right? So here and here. So far clear? Okay, now these are in a scalar form. I write them in matrix form now. Okay, so this becomes this part in matrix form becomes theta transpose kj transpose theta, where kj is defined as kernel matrix of the whole training data and the training data of the jth class. Okay, so it's n by nj. Okay, nj is the cardinality of the jth class and n is the total number of points. Okay, so this becomes this, and also this part, you tell me. So these theta L, theta K in vector form are here. Do you see that? I have these 2 kernels. So I have kj transpose. Do you see that? Also, I have 1 over nj here, which is here. And for the sake of matrix multiplications to match in terms of dimensionality, I have also 1 transpose. What is 1 transpose? It's a matrix of whole ones. Okay, it's different from identity matrix. Identity matrix has only 1 in its diagonal, right? But this has all ones in all of it, right? Okay, now No. If it was identity, it didn't have any. No. 1 is a column vector of 1s. 1 transpose is a row vector of 1s. So the whole thing becomes a matrix of 1s. Okay. Now I factor out, interestingly, I have theta transpose xj, kj here, and kj transpose theta here. Also, theta transpose kj here, kj transpose theta here. So I can factor them out. Left factor out and right factor out. In the middle, this appears. What is this? Recall preliminaries. That's the centering matrix. Denoted by hj. Right? Centering matrix. But hj because it has nj in it. Okay, its size is nj by nj. Okay, then I can bring this theta transpose out of summation because it's not dependent on j. Also, theta can bring it out of summation. It's not dependent on j. Right? So far clear? hj was this. It's nj by nj. Okay. By the way, this one is its dimensionality is nj by 1. Okay. Now, this appeared in the middle. I define it, name it. Name it Benjamin. They named it N. Does it matter? Naming is not important, right? N. It is N by N because this is N by Nj. This is Nj by N. This is Nj by Nj. Right? This is N by N. Then becomes this. Right? As a result, dw becomes theta transpose N theta. Right? Then the Fisher criterion becomes this. Theta transpose M theta over theta transpose N theta. Right? So we maximize this. Again, we maximize this. This is a generalized Rayleigh-Ritz quotient. Agreed? Right? So we can say maximize the numerator where the denominator equals to some constant. Take Lagrangian, take derivative of Lagrangian with respect to theta. This time theta is n-dimensional, not d-dimensional. It gives you this. What is this? Generalized eigenvalue problem. But generalized eigenvalue problem of M and N, not SPSW, right? Agree? But M is related to between a scatter. N is related to within a scatter, right? But in the feature space. Theta is a kernel Fisher direction or kernel Fisher axis. What is the dimensionality of theta? What is the dimensionality of M? It's N by N, right? N is the number of points. What is the dimensionality of N? N by N. N is the number of points. Agreed? So far, did you understand it? Agreed? So what is the dimensionality of theta? It will be n-dimensional, right? Do you see the difference? In Fisher discriminant analysis, the dimensionality of solution was the eigenvector was d-dimensional. Now the eigenvector is n-dimensional. Okay. Now how do we, okay, now assume we found theta. How do we do linear projections and reconstruction? How? Previously we used U transpose X, right? Now we should use phi U transpose phi X, right? Let's see what happens. This is the second important part of the kernelization bar representation theory. In the test phase now. Okay. So now phi U, what was it according to representation theory? Phi U was phi X theta. As a result, phi U transpose becomes theta transpose phi X transpose. Phi Xi is this. Again, this appeared. So the kernel also appears in the test phase. Not only it was used for formalization of training, it was used in the test phase as well. Do you see that? Interesting. So we found theta, which is n by 1. This kernel is also, no, this is 1 by n because of transpose. This kernel is n by 1, right? Also for the test phase, likewise for the test data. So this is, sorry, this is for reconstruction. This is transformation. Reconstruction is phi U transpose phi Xi. Now what happens? Guys, please take a look. This is important. Phi u transpose phi xi we just found in equation 77 is this. Phi u according to representation theory is phi x theta, right? We have theta, we have kernel, we are happy about it, but we have phi x, we are unhappy about it. Do we have phi x? Not necessarily, right? As a result, reconstruction in kernel PCA, kernel FDA is not possible. Do you remember? In kernel PCA, we couldn't reconstruct. In kernel FDA, we also can't reconstruct. Right? Also in the test phase, for test out of sample data, we have like these things, so reconstruction cannot be done. And if we have a bunch of data points to project and project, then rather than one kernel vector, it becomes a kernel matrix, right? This is n by 1, n by n. This is n by nt, where nt is the number of test data points or out of sample data points. By the way, I hope you understand the value of this, because when you read the paper of kernel FDA, you don't see all of these details. Okay, I've explained all of these steps for you to understand what's going on. Otherwise, by reading the paper of kernel FDA, you will not find out what's going on. Okay. So again, that was for one solution. Theta was a vector. Now, what if multiple directions of kernel FDA subspace? Theta becomes a matrix. So I will have trace now. Trace of, so the Fisher criterion becomes trace of theta transpose m theta over trace of theta transpose n theta. Again, the solution becomes this. And now I have several eigenvectors. Likewise, I have a projection, right, for training data and test data. By the way, subscript T means test or out of sample data. Any question? So far we learned how to kernelize our algorithm using kernel tree and kernelization by representation theory. Very beautiful. Okay. By the way, for more information on kernelization and kernels, feel free to read our tutorial paper named this paper. This is a good paper, I believe. Just Google kernel Kojob. So, reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions, Nystrom method, and use of kernels in machine learning tutorial and survey. A part of it has appeared as the chapter background on kernels in our book. Okay. So where were we? Acknowledgement. Some slides of this slide deck are based on our tutorial paper, Fisher and kernel Fisher discriminant analysis tutorial. After we published this in archive, some people implemented that kernel FDA based on our tutorial paper, and that GitHub page became very famous. So yeah, they used the explanation that I just told you. And some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo and Professor Huda Mohammed-Zadeh at Sharif University of Technology. The code, I also have coded FDA. You can see it in my GitHub page in Python. Okay. I have coded FDA and kernel FDA both. FDA or LDA in scikit-learn also exists. Okay. And these are the references. Any question? No? What is the next topic? When you guys say you're tired, I'm double tired. Double tired. But the beauty of mathematics we should forget our tiredness because of the beauty of mathematics. Variational. But honestly, I'm telling you, I'm not just joking. Honestly, mathematics is one of the many cures for depression. Honestly, I'm saying you can use mathematics for getting depression. I'm telling you. No. Honestly, when you go inside the world of mathematics, you will forget the real world. I myself have experienced that. You forget everything. You are walking in the garden of mathematics. Okay, let's talk about factor analysis, probabilistic PCA, and variational inference. One of the important parts of machine learning. Any question? So I can a bit rest. No. Okay. Variational inference. Consider a data set x1 to xn. Assume that every data point xi, which is d-dimensional, is generated from a latent variable zi. What does it mean? Do you know what I'm talking about? Everything that happens in this world is observed data. Okay? Xi, everything which happens, right? But it has been caused by something else. Zi. And that thing is hidden, latent. Right? I'm not talking about supernatural or religious things. I'm not talking about that. I'm talking about metaphysics. Metaphysics in philosophy is different from supernatural. Iranian people, unfortunately, mix them together, confuse them. When they say metaphysics, they mean supernatural. I don't know why. Iranian philosophers make this mistake a lot. Metaphysics in philosophy is completely different from supernatural. Okay. I'm talking about metaphysics. Whatever you see in this world is just the observable thing. There might be some hidden reason for that. Okay. And that hidden thing is a Zi. As you see, here is the connection of machine learning and philosophy also. Okay. The latent variable has a prior distribution, P of Zi. Okay. According to the Bayes rule, it's this. What is this? Probability of Zi given xi equals probability of xi given Zi times probability of Zi over probability of xi. The proof is so simple. You know how it is proved? This multiplied by this equals this multiplied by this. This is a joint of xi and zi. This is a joint of zi and xi. Joint of xi and zi equals xi and zi. Doesn't matter, right? Are you tired? Are you? Okay, let me tell you some story so you get happy. Okay. Forget mathematics. Let's talk about philosophy. I have said it several times. Do you remember? Probability of Zi given. By the way, why am I always referring to philosophy? Because at least several hundred years ago, philosophy was equal to mathematics. You know that. They were completely hand in hand. Philosophers were mathematicians, mathematicians were philosophers. You know, have you heard of René Descartes? René Descartes. Yeah, René Descartes was a philosopher / mathematician. René Descartes proposed dualism. Spinoza, have you heard of him? Spinoza came and said, no, we have monism. Okay. So Descartes was a philosopher, and he was apparently a religious philosopher. Okay. Spinoza was atheist, but he believed in monism and pantheism. Whenever we talk about pantheism in philosophy, it goes back to Spinoza. Okay. And Do you know Cartesian coordinate system? Do you know Cartesian coordinate system? Right? Like this. 1, 2, 1, 2, this to this vector, right? You add the vectors together. This is the total vector, right? Who proposed this? René Descartes. René Descartes, who was a philosopher, proposed Cartesian coordinate system, which has been dominantly used, mostly used in mathematics nowadays. Every high school student knows how to do it, right? So it was proposed by a philosopher. Not long time ago, you know truth table, right? In logic, you say x, y, 0, 0, 0, 1, 1, 0, 1, 1. The x and y, what is it? 0, 0, 0, 1. Who proposed truth table? Wittgenstein, previous century. Wittgenstein was a philosopher. A lot of things in mathematics have been proposed by philosophers. Another example. By the way, another example. This is called posterior. This is called likelihood or class conditional. This is called prior of Z. This is called prior of X. Why do we call it posterior? And why do we call it prior? Because of philosophy. I'm confident about it. I'm not even doubting. Mathematics borrowed these terminologies from philosophy. I can bet. Okay. What are these? What is posterior? It's not an English word. It's a Latin word. It's a posteriori. If you have read some papers in probabilistic machine learning, you must have seen this. A posteriori. Usually they write it in italic. So they tell the reader that this is not a in English. This is not a horse, right? This is a posteriori, and this a is not a in English. This is a in Latin. A priori. These two are Latin words. Let's go back, a flashback to the time of Immanuel Kant or Kant. Immanuel Kant. I bet you have heard of him, haven't you? Immanuel Kant. Kant. Kant is one of the most important philosophers. He has 3 critics. The first critic, the reason that I'm not explaining mathematics because we are all tired. So I'm trying to give you some stories, but valuable stories. I'm not giving you rubbish, okay? Kant has 3 critics. The first critic is critic on pure reasoning. Okay. The second critic of, I think, empirical reasoning. I'm not sure about the name, but something about this. The third one is critic of, I think, judgment, something like that. The first critic is about mind and thought, pure thought. The second critic is about ethics, morality. The third critic is about beauty. Beauty. Okay. In his first critic, how many pages is it? 700 pages. He wrote it in German, although the language of science at that time was Latin. That's why I said these words are Latin. At the time of Kant, the language of science was not English. There was no English now, like nowadays. It was Latin. But people at the time of Kant talked German. So he wrote his book in German. What did he talk about? A lot of things. A big portion of his book, First Critic, was about posterior, a posteriori, a priori, and these things. So in philosophy, specifically in epistemology, What is epistemology? Epistemology is a part of philosophy which talks about whether a proposition is correct or not. What is a proposition? All propositions are sentences, but all sentences are not propositions. Proposition is something which claims something. The pen is on the table. There is a God. Something like this. These are propositions. How are you? It's a question sentence. This is not a proposition. Okay. So proposition, whether we talk about whether a proposition is nonsense and senseful, and if it is senseful, whether it's true or wrong, right? True or false. This is epistemology in philosophy, a big part of philosophy. Okay. In epistemology, we have a posteriori, a priori. I will tell you what these are. We also have synthetic and analytic. 2 times 2, 4 cases. So we have synthetic a posteriori, synthetic a priori, analytic a posteriori, analytic a priori. Okay. Now, what is a posteriori? Posteriori means posterior, means post experience. You understand that proposition, whether it's true or false, after experiencing the world. What is a priori? It's prior, beforehand, right? You understand whether it's true or false before experiencing the world. Let me tell you some examples. The pen is on the table. Is it a posteriori proposition or a priori proposition? It's a posterior proposition because I need to expect, I see the world and see, oh, pen is on the table. Now another example. 2 plus 3 is 5. Is it a posteriori or a priori? What? Posteriori? Why? 2 plus... Can you give me an example of 2 in the world? Do we have the digit 2 in the world? No. We have 2 things. We have things. We have 2 trees, 2 horses, 2 tables. We don't have 2 itself. 2 is a priori thing. 3 is a priori thing. 2 plus 3 is a priori thing. 2 plus 3 equals 5 is a priori thing. We don't need to experience the world. Okay? Okay? Now you see, science is interesting. Philosophy is interesting. Okay, now, what is synthetic? What is analytic? Synthetic, obvious from its name. You need to synthesize to understand. The proposition is a result of synthesizing. Analytic, you need to analyze it. Right? So again, we have 4 cases. Again, 2 cases I think are obvious. Let me remember. Synthetic a posteriori is obvious. Synthetic a posteriori. Pen is on the table. It's a posteriori and it's also synthetic because of synthesis of pen and table. Analytic a priori is so obvious. It's analytic. What is a prior is what 2 plus 3 equals, or something which you don't need to experience. You analyze it in your mind, and it's all a priori. These 2 were obvious. Kant said, why did I say Kant? In English, they pronounce him Kant, but in Persian, they call him Kant. Doesn't matter. Kant or Kant. Kant says, we have a 3rd case too in his book. He says we have, let me remember, he says we have synthetic a priori. It revolutionized philosophy. What does it mean? He said you can synthesize in your mind. Example he mentioned was 2 plus 3 equals 5. For this, you are synthesizing that in your mind. Okay? Although some people didn't agree with him, but still it was interesting. Recently, in the previous century, I think it was Quine, I guess, who said the 4th case is also correct. We have that. We have analytic a posteriori too. He explained some stuff, okay? So that was interesting. But why did I say these? For several reasons. First off, the Bayes rule, the things in the Bayes rule came from philosophy, posterior in this. Also, I mean, at least the names, I mean. Also, I wanted to tell you another example of why philosophy and mathematics were equivalent to each other in the previous. Did you? I just told you Kant, right? Kant was the first philosopher who was a professor in philosophy. Okay, I think he was the first one. What one of his initial papers was it about philosophy? No, it was about mirrors in physics. What is it in? It's not specifically about mirrors. About this, what is that? I don't remember the name of this in English. The things that we use in eyeglasses, convex lenses, and this. His paper was about lenses and mirrors. So he was also a physicist. Okay. Kant had studied Newtonian mechanics. He knew Newtonian mechanics very well, better than physicists. Okay, he was mesmerized by Newtonian mechanics. It impacted his philosophy. Okay, at that time. Okay, I said all of these things, and I also said that truth table is proposed by Wittgenstein. Wittgenstein was one of the first analytic philosophers who talked about philosophy of language. Let me tell you this also, because I think these are very more valuable than machine learning. We have two types of philosophies in general. We have analytic philosophy, and we have continental philosophy. Okay, continental philosophy and analytical philosophy. Continental philosophy is whatever we had until a century ago. Examples of continental philosophers are Descartes, Kant, Schopenhauer, Nietzsche, Heidegger, Hannah Arendt, Karl Jaspers, Spinoza. Many of these people that I just said. Kierkegaard, Soren Kierkegaard. Some examples of analytical philosophers, it started from a century ago. Do you know Russell? Bernard Russell? Russell is very famous. Russell. Gottlob Frege, Ludwig Wittgenstein, Quine, and many of the philosophers nowadays. Okay. By the way, also most of the philosophers in US, in Canada, in England, UK, they are mostly working on analytic philosophy. Most of the philosophers in Germany and Greece are working on continental philosophy nowadays, right? What is the difference between them? They have also difference in subject a bit. So about a century ago, again, another example of what philosopher / mathematician, Gottlob Frege. Gottlob Frege was a mathematician / philosopher 100 years ago. If you read his papers, they are available. You don't know whether you are reading mathematics or philosophy. It's a combination of both. Okay. He talks about functions in a philosophy paper. Functions. You know functions, right? In mathematics. Okay. So Gottlob Frege says some stuff, and then Wittgenstein studied under Gottlob Frege and Bernard Russell. And then he wrote a book named Tractatus or Tractatus Logico Philosophicus. Okay, it means a letter on logic and philosophy, and it revolutionized philosophy by introducing philosophy of language. So beforehand, continental philosophers said that what we first think, and then we use language to transfer it to others. Okay. But analytical philosophers said, Wittgenstein specifically said, no, we think through language. If you take language away from human, they can't even think. Have you experienced that? When you are thinking in your mind, you're thinking in your own language. Right? Some people think in other ways too. Some people think in the language of music. Einstein specifically did that. Whenever he wanted to think about physics, he played violin. Music is a language of notes, right? So you can think of through the language of notes, through the language of pictures, through the language of English, Persian. And now it also, you understand that based on what language you have, your thought process is different. I'll tell you an example. Persian people who only speak Persian, they are not very much good in science. Because unfortunately, Persian didn't improve much in science. Okay. But they are very good in poems, poetry, in emotion. Because Persian is mostly about emotion. The other way around. I think now that I know both Persian and English, the reason that I can think about mathematics is through English, not through Persian. Because English now is dominant in science. You see that? We think through language. So philosophy of language or linguistic philosophy appeared by Wittgenstein, and many people walked after that, like Quine or Keperky or something like that. I forgot his name. Right. Okay. Anyways, why did I say all of these things? To say that philosophy and mathematics are hand in hand. By the way, let me tell you this thing and then I will end. Nowadays, many things that are proposed in machine learning are rediscovery and recreation of ancient philosophy. Let me tell you an example. Have you heard of attention mechanism? I will explain this in the next lecture of deep learning course. Attention mechanism is a thing in natural language processing. It came several years ago. It recreated what Gottlob Frege said 100 years ago. Let me tell you what it is. It says that every word attends to every other words in the sentence. Attention mechanism is, and they use inner product between words in the sentence for that, right? This is attention mechanism. Nowadays, ChatGPT is using attention mechanism. Okay? Because GPT is based on transformers. Transformers are based on attention. Gottlob Frege, 100 years ago, the mathematician / philosopher, said something named context principle. Wittgenstein loved this principle. Gottlob Frege said that the word is important, is related to the context it is used in. An example is that when you talk, the words that you use is different when you talk to a car dealer or when you are teaching in a class. We use different words. The context is important. In other words, every word attends to the context, every other word in the sentence, right? So the context principle that Gottlob Frege said nowadays is used in machine learning. Do you see that? By the way, for more information on relation of philosophy and mathematics, feel free to read my paper on philomatics and psychomatics for combining philosophy and psychology with mathematics. It's available in arXiv. Sorry that I took your time, but I think it was a nice story, and I wanted to share it with you. In the next session, we have one session left, and after that we'll have presentations, right? The next session I will cover variational invariance. What? In the next session I will cover variational invariance, factor analysis, probabilistic PCA, and t-SNE. And if there is any other time, I will cover another topic. If not, I think I already covered a lot of things in this course. But there are some other things which we couldn't go over in this semester, such as hidden Markov model or local linear embedding, isomap, and these things. But they're available on my YouTube. You can watch them. And also feel free to ask me if you have any question about them, and I will be happy to answer you.
Where is your YouTube video for these courses?
You go to, just give me a second. So here it is. It's my YouTube channel, right? You go to, so these are the videos. By the way, this is my second YouTube channel for about my points. Okay. You go to playlists and you see all of these courses here. Optimization techniques, winter 2023. The data and knowledge modeling, I was TA there. Dimensional reduction. Statistical machine learning, last semester, the spring or summer 2020. Deep learning of last semester. Computer vision, I have talked about. Adaptive and cooperative algorithms in the University of Waterloo. I talk about meteoristic optimization, game theory, reinforcement learning, and fuzzy logic in it. It's kind of a soft computing course. Statistical machine learning this semester, deep learning, and software engineering. I talked about Python here. No problem. Yes. Yes. It's not possible. There is no class. I mean, the class. No. The e-access will lock the door. I think because I remember at the start of previous semester we had the issue. I was lucky that I came sooner and I could let others in. Otherwise, we would be locked out. The e-access will only leave the doors open. The e-access of the, because these have yeah, just let me stop this.